Hello everyone, welcome to another episode of Talkative Strangers. Today we have with us Juan. Would you like to tell the audience a bit about yourself?
Thank you for having me. Yes, well, my name is Juan. I was born and raised in Venezuela and got my undergraduate degree in physics and computer science at the University of Texas. And I'm about to start my PhD in physics at the University of New Mexico. And
Okay.
can't wait to talk about physics with y'all.
Okay, that's
Yeah,
great.
we're looking forward to that. So,
Right.
why physics? Like you're doing your PhD in physics. Why physics? Why do you love physics so much?
Yes,
That's
there's
a-
a reason for that.
That's a good question. Well, I did high school and I wasn't motivated at all. I just studied to pass and just be over with it. And so when I moved here and I registered for college, they were like, "What do you want to major in?" And I said, "Well, I like being around computers a lot, so just put computer science." And that's how I started. And I did 3 years like that. And then just one summer, I was walking around the library and I saw a book that was like Introduction to Quantum Mechanics that caught my eye. It looked interesting. So I grabbed it and I read it on the bus every day on the way to class. And I started watching YouTube videos on things and I was like, if I don't study this, I'm going to regret it. So I added it. I didn't know what I was going to do with it. I didn't even know what a PhD was because in Venezuela, research is non-existent. I don't know how it is in India, but it's not a thing. Like
No,
nobody.
In India, there also no research is being done. Majorly.
Yeah. So I had no idea what a PhD is. And to this day, I still have to explain to family like what it is because I learned all of this like 2 years ago. So I didn't know what I was going for. I just knew I liked it and I was like, I gotta keep studying it. So that's what I'm doing.
Okay, that's great.
So you talked about quantum mechanics. So many people don't even understand the word quantum. So can you tell what exactly does quantum mean?
Yeah, so that word was introduced by Einstein. So for a long time, light was thought of to be, well, there was a big debate. People didn't know if light was a particle or a wave. A long time ago, Newton, he released kind of like a book, Newton, where he said that light was made of particles. But then everyone, when people started learning more about electricity, magnetism, they realized no, light is an electromagnetic wave. Newton was wrong. But then there was this, yes, the Maxwell's equations, exactly.
Yes, he said that.
And so people were like convinced that light was a wave. But then there was this one experiment called the photoelectric effect that Einstein was the one that was able to give the explanation because this experiment was not in accordance to what the physics said. People said, oh, light is a wave, then this should happen. But the photoelectric effect, something else happened. And Einstein said, no, if we think of light as packets, like particles, which he called quanta. So quanta is like a little packet of light. So it's discrete units. It's not a wave. It's not a continuous wave, but it's divided into packets, quantas. Then this makes sense. And here's the physics for it. And this is what got Einstein his Nobel Prize. And from there, was one of the discoveries that started quantum mechanics. It's about thinking of things as not continuous, but separated into quantas or little packets.
Packets of energy, basically.
Like what?
They are little packets of energy. The quantas are.
Yeah. Mm-hmm.
So when you project some and you give some energy to them quantas, and they basically get excited and reach the upper state. There's some threshold energy also involved in that.
Yes. So I think you're talking about like the energy levels in atoms. Is that right?
Right.
Yeah.
The excited.
Yeah. That was another. So there was it 3 phenomenons? So the one that I'm talking about is the photoelectric effect. There's another one that was what really started everything called the UV catastrophe. And that is where people learn that atoms only received energy and different energy levels, that there's no in between. It's either this orbit or the next orbit, but you can't have energy in between. So there's energy levels, like what you just said.
Discrete energy levels. Okay. Right.
Yeah, and that's how quantum mechanics started. It's just thinking of things. We used to think that everything in the universe was continuous, because that's in the big picture. Everything looks like, oh, I can move my hand anywhere. There's no like, oh, I can only have it here or here. There's always in between. And we thought everything was like that. But then with quantum, we realized that that's not true.
Okay, so you like quantum mechanics, and quantum mechanics is also related to quantum information and quantum computing. So
Yeah.
what's the difference between a normal computer and a quantum computer?
That's a great question. So regular computers work with bits. You have
Right.
something.
Zeros and ones.
Yes. So it can be anything that you can have in two states, which in theory we call 0 or 1. One phenomena of quantum physics is that things can be in superpositions. And what this means is that they can be in several locations at the same time, which is not intuitive. It makes no sense if you have never heard of this before. Like, I'm either here or I'm not here. I can't be here and in another place at the same time. But in the quantum world, so really little things can be in superposition, which makes the possibility of a bit being in 0 or 1 or both at the same time, some superposition of both of them. And this is what sparked the idea behind quantum computers, because we realized that there are some algorithms that can be done in less steps if you're able to work with a superposition in a clever way. There's only a handful of quantum algorithms, because it's really hard to find applications where superpositions and other quantum phenomena help you do it faster.
Okay.
Does that make sense? I can explain any of that if I kind of... If
No,
anything
that's
doesn't make
not.
sense, let me know and
Yeah.
I'll explain it.
No, it's not a problem.
But how does superposition help in a certain way? Because superposition is just like, it's also 1, it's also 0, or it's somewhere in middle. So how does that benefit in any way?
That's usually the question I get the most, but it's really hard to explain it without math, because this wasn't even apparent. Like, quantum mechanics started in the 1920s, 30s. It was a long time ago. But quantum computing only started in the past 30 years. Because even after we learned about superposition and all that, it took a long time for people to realize, oh, we can use a superposition to do things faster.
Right.
And it's about being really clever and doing a lot of things. It's a quantum algorithm. So it's several steps where you show, hey, this is done in less steps than the normal algorithm. So for example, I can give you an example of one of the quantum algorithms. There's only, I think, around, is it 5 right now that we have? So ever since we discovered all this, we've only been able to think of a handful of quantum algorithms. That's because it's really hard to find applications for it. They're very specific things that you can do faster. So to give you an example, let's say you have 5 boxes, and I tell you there is one ball in one of the boxes. What would be the best algorithm you can think of to find the ball fast? The fastest way to find that ball.
That ball.
Open each and every box and...
You just go through the boxes, right?
Yeah.
Like, you go through the first one, check it. If it's not there, you go to the next one, check it. If it's not there, you go to the next one, check it. And you keep going until you find it, because you don't have any information. There's no better way. You can think about this for 100 years, and you will not find a better way to do this, because it's such a simple problem. But superposition is such a weird thing, or the quantum phenomena, because it also requires... Go ahead.
Yeah, so superposition we can open every box at same time.
Yes. Okay.
Okay.
So that brings a good point. I'll come back to that. So in let's go back to the normal example. You have the boxes and you're checking one of them. On average, you're gonna check half of the boxes before you find it, right? Because it can be at the end. And if you place the ball randomly, you're gonna find it sometimes at the end, sometimes at the beginning. And on average, you're gonna take half.
Right.
Right? So it's always half. And there's a quantum algorithm that is square root of half of the time to find the ball. Okay.
So it's something less than that.
Yeah. So you do it in less steps.
Okay.
So on average, instead of searching, if you had 4 boxes, well, that would be the same. But if you had 5, you're looking at 2 or 3 boxes. This would be square root of 5, which is a little bit less. Okay, so now you said a good point that you can check all boxes at the same time because you're in a superposition. Sure,
right.
That's fine. You read this a lot in like news articles that are talking about quantum computers. They're like, yeah, there are computers that check every possibility in parallel worlds at the same time, so everything's faster, which is kind of true. Half of it is true, where if you check all boxes at the same time, you're in a superposition. But something that's not good for computations is that if you go ahead and measure, you're going to find randomly one of the boxes. You can't check all the superpositions. So now let me unpack that a little bit. If you have a normal bit, a class from a normal computer, 0 or 1, if you check it, it's going to be either 0 or 1.
Right.
If you have a superposition between 0 and 1, you have some probability of seeing a 0 and some probability of seeing a 1. But when you go ahead and look at it, when you measure it, you're not going to see it, the superposition. You see either 0 or 1. You see the same thing than with a normal computer. So if you did your superposition over all the boxes and you measured, you're just going to randomly check one of the boxes. So it didn't help you at all. You ended up with the same problem. So it's about being
a possibility that you cannot find a ball, but it's still there.
Yeah, so if you did that, that would be the same n/2 or 1/2 of the boxes that you need to check. You would be doing the same thing that you did classically. So it's more complicated than just putting it on a superposition and measuring. That's why it's an algorithm. And that takes more math to explain and to look at it.
Right.
But that is the essence, that you do have the ability to put in a superposition, but then you have to be clever enough to make the probability of the empty box be closer and closer to 0, and the probability of the box with the ball getting closer and closer to 100%. Or to 1, yeah.
So the main problem they are facing right now is to make an algorithm to use the quantum computer.
There's a lot of problems right now.
Okay.
Yes, that is one of the problems, is that we don't have enough algorithms. So that's why right now there's a lot of hype. Like, there's a lot of people putting money into it, governments, private companies. I currently work in a private company that is for quantum computers. And they're all like, yeah, quantum computers, they're going to revolutionize the world and all that. And we do know that they have a lot of good applications, but it's only a handful of algorithms right now that we can do faster. There's not a lot, especially not if you compare it to all the money that's been thrown into it. So yes, we do need more algorithms. That would be great. But it's also an engineering disadvantage right now. It's really hard to keep a system in a superposition. It kind of, the word is decoheres. And that kind of just means that the superposition goes away. So in order to do that, the engineering needs to be really good, and quantum computers are getting better every day. But I think right now the biggest one we have is like 50 qubits. So if you compare that to the computer you have in front of you, it probably have 8 gigs of RAM minimum, and that's 8,000 bits. So yeah, that's way more than what we can do with a quantum right now, a quantum computer.
Okay. And I read somewhere that in quantum computer, the circuits are extremely small. They're the size of an atom. So how does that help in any way? If it's small or it's big, what does that matter?
Well, so
They might consume less energy for that.
What is it?
They might consume less energy for that matter.
Yeah, less energy.
Keeping the cell small.
But are you saying that the chip is small, or are you talking about the qubits? Or do you remember what you read?
The chips, the circuit, mostly everything is extremely small.
Yeah, so the thing about the superpositions is that the less things you have involved, the less particles, the easier it is for it to stay in a superposition. If you have it interacting with other things, then it decoheres. It goes away, basically. So the thing is, what do we make a qubit out of? Like, if you think of bits, bits can be made out of anything. We have some right now. The most that we use are transistors, but you can make a switch, a bit. I have here a container. This can be a 1, and this is a 0. That's a bit.
Right.
Just like that, we can make qubits out of a lot of things. And we choose to make them out of really small things. Well, one, because of space, but also because it's easier to keep a quantum state quantum if it's really small. So atoms, there's some atoms that are used as qubits. So qubits is a theoretical thing, an abstract. And then to make it physical, you need to choose something to make it out of. Does that make sense?
Okay.
Yes, kind of.
A little bit.
Now it's making better sense about the quantum realm.
Yeah.
So, who proposed this, that we can basically involve quantum and computer? How a person can combine those two things?
That's another good story. That was Feynman. Have you guys heard of Feynman?
Richard Feynman. Feynman.
He's a famous physicist.
Richard Feynman, yes. Yes, I heard that.
He actually proposed this before he realized there's some algorithms that we can do faster. Well, is that correct to say? So here was his idea. If you have 1 bit, it can be 0 or a 1, and then for each possible state, you have some probability, like I explained, right? So you have some probability of 0 and some probability of 1. So if you're trying to simulate that on a computer, you would have to store the probability for the 0 and the probability for the 1. So you already have 2 numbers for 1 bit. Okay?
Right.
Now, if you go to 2 qubits, quantum bits, then you have the probability of both of them being 0, one of them being 0, one being 1, both of them being 1, and then 0 and 1. So you have now 4. So for 2 qubits now, you would have to store the probability of each of those states. If you go to 3, now you got 8. This increases exponentially. So if you try to simulate this on a regular computer, this quantum system, it would take an exponential amount of space or time.
Right.
So he said, why don't we just make a computer made of quantum parts to simulate itself? Just like if you're trying to simulate what would happen if, this is a common analogy, if you're trying to simulate what would happen if you throw a teapot, just a pot to make tea, if you throw it and it crashes on the floor and it breaks. If you try to make a simulation for that, it might take you a long time, maybe it won't work as well, but if you just grab a teapot and you throw it, then that's the best, that's better than any simulation. So he said, let's just use quantum systems to calculate quantum things. And then is that people realize, oh, but aside from just quantum simulations, we can, people started realizing there's algorithms that would take less steps than normal algorithms. But that's how it started. Yes. I think it was in the 80s or the 70s.
And the IBM was the first company to make that, the quantum computer.
What was the first quantum computer? Is that what you said?
No, IBM made the first quantum computer.
Yeah, I'm not sure who made the first one. I don't know. I know that right now, yeah, it's IBM, Microsoft, and Google fighting.
Okay, so are many companies currently working on the quantum computers? Do they think that that's the future, or they think that it might not develop in? It might take two to three centuries to basically get to know more about that. So they are not investing.
Well, I don't know. I don't know much about like how long it will take, because that's more of an engineering problem. But there's a lot of people betting that's going to happen soon, and they are increasing the qubits really soon. Like we have 50 something right now. We had, I think it was 30 2 years ago. So they're going fast. And who knows? There's also a lot of different quantum computers. As I said, you can choose what to make a qubit out of. So there's some people trying to do atoms, trying to do ions. What else? Oh, the Microsoft doesn't even have an actual quantum computer, because they're trying to make one out of qubits that people don't even know how to make physically yet.
Right.
And they're, if they were able to, they would be better than everyone else's, because that's the theory says so. But they have no idea how to make them, and they're putting all their money into it, and they think it's possible. So
so they are basically investing. All the major companies are actually investing in the quantum computers.
Yeah, it's a big race going on right now. Yeah.
When do you think a normal person like us might have a quantum computer at their home?
Well, okay, the consensus between scientists is that we won't have quantum computers, because like they're not better than classical computers on everything, and they're much harder to make. But it is a possibility that your computer in the future might have a quantum sector, like a quantum device attached to it. So you know how like you have a RAM and a GPU, maybe you will have a quantum processor on your computer. So it might be what's called a hybrid.
Right.
And that's a possibility. So for example, if you were trying to run the algorithm to search for the ball in the boxes, that would run on your quantum processor, since that would be faster. But for anything else, or not anything else, maybe you would have the five algorithms run on that, but everything else would run on your normal processor. Yeah.
It will be a mix-up of hybrid of two computers.
Yes, that's
quantum one and the normal one.
If it ever becomes really easy to make.
Right.
Yeah.
No, well, it might become in 30 to 40 years, that we can expect at least.
Maybe. I mean, we haven't theorized any qubits that would be easy to make. Like most of the quantum computers we have today, they need to run at, what was it? 0.03 Kelvin. It's either that or 0.3 Kelvin. Kelvin is measurement of temperature, where zero is no temperature. Absolute zero is everything's completely still, which is not possible. So you cannot reach zero, you can only get close to it. So it's crazy low temperatures. So that requires a lot of power to have that good of a fridge.
Right.
But yeah, I think it's really low. I don't want to repeat any numbers because I'm not sure, and they all work differently. But yeah, it's really, really close to zero. So we don't have a better way to do it. We're just making more of those right now. But if we ever find out a way, maybe.
Anything is possible.
Yeah.
Yes, that we can expect and hope.
And I checked out IBM's website, and a normal person like us can use a quantum computer.
Yeah.
So what can we use it for?
Um, well, it all has to be small problems. So things with only maybe a max of 5 variables. One thing, there's a YouTube video explaining how to use their computers to make like a calculator. You can make like a quantum calculator to add numbers. These numbers can't be very big. I think they can go up to maybe 16, but you can do that. So, or you can implement the search algorithm that I told you for the boxes, and then you choose where to put the ball and run it on the computer and see how long it takes it to find it, and things like that. So there's like the classes I've taken, they've had us implement all the algorithms we currently know and run them on the quantum computers. Yeah.
It's kind of a simulator.
A simulator? Well, what do you mean a simulator?
So the quantum computer that we're using on our normal computer is kind of a simulator that we're using. It's not the actual one, but it acts
It's the actual quantum computer. You can, if you download their software, IBM has something called Qiskit, which is in Python. And you can choose if you want to run it on a simulator or if you want to run it on their actual quantum computer.